Sounds great. Thank you, John. Thank you, everyone, for being here tonight. Goal is to get through as much as possible. As you may have seen on the slide deck, there are like close to 250 slides. So you will have access to this slideshow. Actually, I don't know if I have a way to share that, but it's already on my bio linked in there. So you have access to all of these as well. So anything we don't cover, you are welcome to review this and you will have access to all of this. So let's get started. I'm Corinne. I run Chem with Corinne. I'm a former AP chemistry student, teacher, tutor. I've done it all. I'm happy to be here sharing all of the tips and tricks I've learned over the last couple decades. And as John mentioned at the beginning, I'm coming to you from Central Virginia. I did my graduate work over at UVA. I'm close to UVA. If anyone's interested in going to UVA, I'm all for it. I have 2 degrees from University of Virginia. So goal for this session, we're going to focus on the big ideas tonight. Hopefully you know all those little nitty-gritty details, and we're just going to focus on the big ideas that you will see in multiple places on this exam. I want to make sure we're still actively engaging with practice problems because that is the best way to get ready for tomorrow's test. And I want you to feel more confident in your content knowledge. And then I'll also just answer your questions. I know the chat is blowing up right now. And I will check that as we go. And I'll also stop at different points so I can catch up with anything. And I think I noticed before the session even started, a lot of you were spending time answering each other's questions. That's awesome. We are a team in this, right? Everyone's saying we're all feeling cooked, right? Right now, maybe you're feeling overwhelmed with certain content, certain aspects of the content, feeling more confident with others. Help each other out. We are a team tonight and tomorrow. So let's get started with those big ideas. We're going to talk the greater effective nuclear charge. We're going to talk Coulomb's law, polarizability, and intermolecular forces. So let's just get started. So when I'm talking about effective nuclear charge, what is that? This is one of those buzz phrases that College Board tends to like, and you've probably been warned about this from your chemistry teacher. And basically, it's just this idea that the greater the number of protons in the nucleus, the more the electrons are going to be attracted or pulled inward towards that. And this is going to be what is responsible for all of those periodic trends. And whenever you think about periodic trends, this will come up later in the session. You want to be really careful not to say, oh, yeah, the atomic radius is bigger because it's to the left of this other element. No, you need to explain what's actually going on. And effective nuclear charge is one of those concepts that's going to explain all of these trends. Other thing you need to really focus on is Coulombic attraction. I've been seeing this a lot, and this is what I normally say too. You want a 5 tomorrow? Mention this as often as possible, right? So Coulomb's law is just this idea that the force is going to be proportional to the magnitude of the charges of different ions and then inversely related to the square of the distance between them. So basically, right, the bigger the magnitude of charge, the stronger the force of attraction or repulsion, and then also the smaller the distance, the bigger the force. It's kind of intuitive, right? But a lot of students get tripped up on this because you see Coulomb's law and you're like, what is going on here? If you can just remember those relationships, that's going to determine all of those periodic trends. So know what these two things are that we can then relate back to all of those simple things. So just this idea that if ions have opposite charges, they're going to experience an attractive force. If they are alike, which means they both have positive, both negative, they're going to be repulsive forces, right? All of this is really, really straightforward. Yet this is how you get points tomorrow. When you sit down to take that FRQ, you need to be able to describe and explain what's going on. And using the phrases like effective nuclear charge and Coulomb's law are the phrases that you need for those points. All right, the other big buzz phrase is polarizability of the electron cloud. And a lot of students know, okay, it's going to be more polarizable if it has more electrons or it's a bigger molecule. But what's going on? What does this even mean, right? So polarizability of the electron cloud is just the tendency of that cloud to become spread out or distorted. So when that happens, right, you're going to have electrons in one section, leaving a positive charge over in the other section of that electron cloud, creating temporary dipoles. So those dipoles are going to change your IMF, they're going to change your reactivity, and they're going to increase your solubility in water. And that's why this idea is so important with IMFs, because IMFs are like 22% of the exam. So if you're able to explain what's going on using these terms, you will get those points you need on that FRQ tomorrow. So how will you use polarizability? Again, when you're comparing the strengths of the intermolecular forces, you want to figure out which is going to have the more polarizable electron cloud. And as I've already hinted at, you can determine that based on the size of the molecule or even just the number of electrons. So if we're comparing, let's say, H2S and H2O, both are going to have those bent geometries. The difference is sulfur is going to have more electrons. So because H2S has a more polarizable electron cloud, it's going to experience stronger London dispersion forces. And we're going to hit all of those intermolecular forces because you do need to know those tomorrow. All right, what questions do you have? Let me check out the chat. I love seeing where everyone's coming from. Yeah, I am very close to Northern Virginia. Seeing a lot of that. Chicago, California, New York. Awesome. Thank you all for being here tonight. Let's see. Anything related to what we just, okay. Vesper. We'll get into Vesper. You're not going to see a lot. You don't really have to memorize it. You don't really have to know the angles. And yeah, you won't have to do any calculations with Coulombic attraction, but you need to know those relationships between those. So yeah, so really you don't need to memorize Vesper. If you know like the top four geometries up through tetrahedral, you should be good. You should not need the angles. So everyone's asking about Vesper now. Yeah, don't focus on that. That's not what you need to memorize tonight. I will tell you exactly what you need to memorize. And what do you say instead of like dissolves like? Yeah, that's going to come up later in this presentation too. So let's keep going. And when do we need to talk about the polarizability? That's when we're talking about intermolecular forces. So a lot of times you'll be given a prompt that will say, okay, this compound experiences London dispersion forces. This one experiences both the London dispersion forces and dipole-dipole interactions, yet the first compound has a higher boiling point. Why? If that's the case, it's polarizability of that electron cloud. It's going to be a larger sized molecule, or it's going to have more electrons, and therefore, in that case, the London dispersion forces are actually going to be stronger than dipole-dipole interactions. Yeah, and no, you don't need to know the quantitative equation. That's why I just said the force is proportional. So it's just this idea that magnitude of charge, it's a direct relationship, and then distance between charges, that's going to be an inverse relationship. Yeah, and polarizability just refers to how far that electron cloud gets distorted. That's what that means. You don't really need to know that, but I like understanding why do we care about this term, right? So that's why. All right. Next set of big ideas, Q versus K, thermodynamic favorability, and rate laws and IMF again. We're going to keep hitting on IMF, kind of a constant theme considering it's almost 1/4 of the exam. So Q versus K, this is a big one. Q is going to be the reaction quotient, which is the reaction when it is not at equilibrium yet. So you're still going to calculate Q in the same way you calculate K. The difference is K is going to be the equilibrium constant at equilibrium. And notice that you're right, you don't include solids or liquids in this. So remember that. So let's look at the difference. How can I use each of these? So the direction the reaction is going to shift to reach equilibrium will be determined by Q. Okay, if Q is less than K, the reverse reaction is going to be favored. If Q is greater than K, the forward reaction is favored. If they are equal, the reaction is at equilibrium. And I had a student last week who told me, which is genius, I don't know how I've never noticed this. The equal sign or the greater than or less than sign points in the direction that the reaction is favored. That's great, right? So Q less than K, you're favoring that reverse reaction. Q greater than K, the forward reaction. Versus when the reaction is at equilibrium, K is going to tell you which reaction, again, is favored. K is greater than 1 or K is very large, forward reaction. K less than 1, reverse reaction. K equals 1, that means your concentration of products and reactants are equal. All right, so just thermodynamic favorability, I would memorize this as well. So you need to know what is favorable, and that's going to be a negative delta H, a negative Gibbs free energy, and then everything else is positive. So if you can remember which ones are negative versus what is positive, that will help you out. The other quantities, so entropy is going to be positive, K is going to be large or greater than 1, and then cell potential, that E dot cell thing, that is going to be positive, and we'll get into cell potential towards the end. Yeah, and I like the Pac-Man idea too. Which one is Pac-Man eating, right? That gives you an idea. Yeah, what is Q and K? So Q is, again, the reaction quotient. It's going to tell you just kind of where the reaction is in terms of approaching equilibrium, versus K is going to be the equilibrium expression. It's just the relationship between the products compared to the reactants. And that can be measured based on the concentrations or the pressures if we're talking about gases. All right, let's continue on. So know these so that you can answer all those questions. The other thing I would memorize tonight are just these rate laws. So this is just going to give you an easy point or two if you can remember this. So if we graph the relationship between the concentration of A versus time, and you get a linear slope that's a zero order versus the natural log of the concentration of A versus 1 over the concentration of A. So when you're doing rate laws, you are looking for those linear graphs, and that's going to give you the order of the reaction. And then I think a lot of people have been concerned about this, but if you're given a bunch of steps of a reaction, the slow step is going to determine everything. You'll use Hess's law, you'll just add things together. These can be a little bit overwhelming because you might see a lot of different reactions, but it's actually pretty simple just to add everything together. So don't get stressed out with rate laws. Yeah. Let's see. Let's keep going. And then the other big ideas are just going to be intermolecular forces. So IMF, IMF, IMF. So important because, as I said, it's almost a quarter of the entire exam. So make sure you feel really solid with these. So IMF, just knowing the differences between those. I think I've linked flashcards here so you have access to those so you can practice with all of these. But just knowing what is required to form a hydrogen bond, you have to remember that it's hydrogen reacting with a very electronegative atom, so fluorine, oxygen, or nitrogen. But the hydrogen has to be in a polar bond. So if it's hydrogen bonded to carbon, you're not going to have a hydrogen bond there. So be really careful with that when you're trying to figure out where a hydrogen bond will form. And it is pretty common to see on the FRQs, like draw in where a hydrogen bond would occur. Really, really easy point. But you got to make sure that the hydrogen is in a polar bond first. When we're thinking about the strength of the molecular forces, typically hydrogen bonding is going to be stronger than dipole-dipole, which is going to be stronger than LDF. As mentioned at the beginning of this, though, we will have instances where LDF will be stronger than dipole-dipole due to the polarizability of the electron cloud. Again, you're pretty much going to be told when that's the case. You're not expected to know when that's going to happen. But if you're told that's the case, you need to be able to explain why. Again, polarizability of the electron cloud. And dipole-dipole, the strength of those is going to be based on the strength of the polarity of that, how polar the molecule is. So the more polar it is, the stronger those dipole-dipole interactions are. Because again, the greater, right, the difference in those charges. Let's see. I think, yeah, and when you just think of intermolecular forces, if you can just get this relationship in your head, right? The stronger the intermolecular force, the higher the boiling point and the lower the vapor pressure. And this is all because the stronger those interactions are, therefore, the more energy it takes to disrupt those interactions in between molecules. Be careful too, intermolecular versus intramolecular. So intermolecular, I'm just talking about the interactions in between molecules versus intramolecular, I'm looking within that compound. So looking at all of these water molecules drawn on the screen, intramolecular would be the covalent bond between hydrogen and oxygen, the polar covalent bond. Let's see, let me check the chat again. Yeah, H bond is technically a dipole-dipole. Yeah, but you should mention them separately because a lot of times you'll have something that will have everything has LDF, right? Everything has London dispersion forces. If you have polar bonds, then you'll have dipole-dipole interactions. In addition, if those polar bonds, you have a hydrogen bonded to fluorine, oxygen, or nitrogen, we can further classify that as a hydrogen bond. All right, let's see. Yeah, and you can use Le Chatelier. And we'll do, let's see. Sorry, I'm trying to keep up with all of this. There's a lot in the chat right now. This is awesome. As if I miss things, feel free to respond. If you know the answer to something, feel free to respond. Like I said at the beginning, we are a team in this. We have just a few hours to go until the exam. So if you can help someone out and catch something that I have missed, please do so. Let's go ahead and continue on. I want to make sure that I can keep, let's see. So let's continue on to equations not on the sheet, because this is often something that everyone's stressing out about right now. So you should feel really confident, right? Understanding the equation sheet. Know that tomorrow when you go in, unfortunately, when you take the FRQ, you don't get to pull it out of your booklet. So what I suggest is bring in an extra pencil tomorrow or just dog ear the corner, right? Fold over the corner to make sure that it's easy to flip back and forth to that. These are the equations not on the equation sheet. Most of these are just, I've just moved things around. But tomorrow, time is money, right? So you want to make sure you're not spending time doing the algebra and you're just focusing on getting your answers written down in that booklet. So these are some of those equations. And if you look, you should be able to access this list of equations too. I've been sharing this for a couple weeks, but the big one is going to be the cell potential. That's not on there at all. So make sure you know that. And I do want to get to some practice FRQs and things like that. All right, so other things to know, solubility. Focus on what's always soluble. Don't worry about everything that's not soluble. If you know what is always soluble, you can answer any of these questions tomorrow. So group 1 ions, potassium, sodium, all of those. Anything with ammonium, NH4+, the nitrates, NO3-, and the acetates. You should also know those polyatomic ions. That's something that I do recommend memorizing because it's just going to save you time again tomorrow. So if you haven't done that yet, spend 10 minutes tonight just going over those. There's so many free flashcards out there to help you with that. All right, other things, assume the 5% rule always applies. Despite what your teacher has told you, you do not even have to justify your answer on the FRQs. So if you just go through and you just calculate everything, you cross out X from the start, you will not lose any points, okay? As long as you're showing all of your other work, you are good. So just assume you can always negate X. So we're going to assume that K is always going to be very small. And that means that a small percentage is ionizing compared to the total. So just assume the 5% rule always applies. Also use 3 sig figs throughout the exam. So there might be one question on the entire, there will be one question on the entire exam that is going to be a sig fig question. Everything else has a tolerance of +or-1. So 3 is always a safe bet. Let's see. What not to say on the exam is just as important as knowing the buzz phrases. So let's talk about some of the things not to say. And I think someone brought this up. Someone said, like dissolves alike. Yeah, do not say that tomorrow. You can think it as you're sitting there, but do not use this to actually justify an answer. So what you want to do instead is focus on solubility and the polarity of those solutions. So we could say, okay, instead, both of these substances are polar, therefore they're going to be miscible. So miscible just means they dissolve within one another. So even if you just say they're both polar or nonpolar, that's enough to justify your answer. Do not say like dissolves like, because the readers are going to look at that and, well, what are they like? Right? You always want to be very specific. Use the terminology when you can. All right. Other things you need to be careful with are just particles. If you don't know whether you are talking about an atom or an ion, a molecule versus an atom, don't mess up mass versus mole, but it's so common. Just be careful with these. If you don't know what to refer to it as, just refer to it as a particle. A lot of times the name of the particle is not going to be part of the points that you are receiving. But if you make a mistake there, that is going to bother the reader, and you will lose points for that. Okay, so if you aren't sure, just refer to it as a particle. All right. Okay, based on the periodic trends. So you do not want to ever say that something is based on the atomic radius or electronegativity trend. So, for example, you do not want to say sulfur is located to the right of phosphorus and therefore has a smaller atomic radius. Instead, focus on what we talked about at the beginning. So, sulfur is going to have a greater effective nuclear charge as it's going to have more protons in its nucleus compared to phosphorus. So, therefore, sulfur's valence electrons will experience stronger Coulombic attraction and will require more energy to remove. Use those buzz phrases to justify those trends. Again, the ideas behind the trends are relatively simple, but you can't just say, oh, because the arrows go this way, I know. Yes, you can use that in your head to keep track of those trends, but again, you need to make sure you're using the terminology as you justify that. All right, let's see. Are there any other phrases you've been told to avoid? I don't know if I've missed anything. Again, help each other out. Let's see. Let's see. How would we know if 5% of it dissolves? So you're just going to assume 5% rule is just saying that we're negating X. We're assuming that X is, so the percentage that has dissociated is so small compared to what we have started with, our initial concentration, that we can just ignore it when we're doing those ice tables. Let's see. Electrochemistry, polar. Yeah, substance, if a substance is polar, that's going to be a difference in electronegativity. Let's see. Yeah, avoid like dissolves like. Um, yeah, always use units. Absolutely. Hopefully you have been told that all year long, right? What's the point of a number without a unit in chemistry? Um, yeah, it and that, avoid that. Shift left and shift right, yes. Forward versus yes. So talk about instead of shifting forward versus reverse, talk about what is favored. So we're going to favor the products or make more products. We're going to create more reactants. These are all great suggestions. Thank you all.
Great. And hey, everyone, it's John from Marco. If you are enjoying this video, go ahead and press that like button. Real quick, we realized, Corinne, I don't have the link to these slides. We have the link, so I'm going to add this to the chat and the description. I don't know if you can take a moment real quick and grab
Yeah.
that link and put it in our Zoom chat. I'll share it out with the group. Um, and wonderful. So I'll take care of putting that in the YouTube chat, and everyone, I'm going to add it to the description. So yeah, and it looks like there was, if there were any other questions, go ahead and share those now. Or this is a really good point that you've put on the slide, Corinne, which is about these descriptions and phrases that we've been told to avoid and sort of tackle. So wonderful. Thank you all for coming. By the way, this is the second of the 18 live reviews that we're hosting at Marco Learning over the course of the next couple of weeks. So keep us posted in this chat and throughout all of our videos about how we can help you the most. So Corinne, I'm going to go ahead and share this slide. Yeah, and we'll make sure that we link the link for the flashcards. Is that in the slide deck,
It
Corinne?
is. Yeah, I have a
Great.
bunch of links and it looks like I had a typo in something and I totally missed it and I cannot keep up with it.
That's okay. They'll
There are
hold you
probably
accountable
typos
in the
and it
chat.
looks,
They'll let
yeah,
you
I
know.
appreciate it. Just like you guys, I think we're all overwhelmed this time of year. So if I've made a mistake, please feel free. If you have the link to the slideshow, please like leave a
Yep.
comment on that too, so I can fix that. And I totally missed that. I'll go back to that after this and I will fix that. All right, let's continue on. So my plan here is just to focus where you guys, I'm trying to read through the chat right now to get an idea of where we should focus. It looks like a lot of people are concerned about Unit 9. Um, so let's see. So I think that's probably where I'll start, and then I'll go into Unit 8 because that's where I would anticipate most of you are struggling the most right now. So let's go ahead and go into Unit 9. And again, if you have access to these, all of these units are linked directly to the slide, so you can jump in and just review the content where you need to. Yeah, so we'll do Unit 9 and then we'll do Unit 8 for sure. All right, and the good thing about Unit 3 is it is in everything. So as we go through Unit 9, we'll also hit on those concepts from Unit 3 as well. All right, so looking at those big ideas, Unit 9, it's all about entropy, Gibbs free energy, and thermodynamic favorability, coupled reactions, and electrochem. Looks like a lot of people are asking about electrochem. So let's skip ahead to that if I can. Let's see, there's a lag now, of course. Let's see. Um, Looks like my screen has paused. Okay, we'll try this again. So with Unit 9, you want to feel really confident with the calculations like this, right? This is entropy. Any of those situations where you're calculating the sum of the products minus the reactants. The exception there is bond enthalpies, where you'll look at bonds broken compared to bonds formed, which technically is reactants minus products. So just be careful with that, so that you know that distinction. Everything else, delta H, delta G, it's always products minus reactants. So this is just a sample. I'm going to skip ahead to electrochem. I'm trying to move too quickly, I guess. All right, coupled reactions. Should we go through that? Entropy? Okay. All right. We'll go backwards. We'll do entropy. All right, so with entropy, everyone hears that entropy is a measure of disorder, right? That's not a great definition. What you want to think about is entropy is actually going to be a measure of how diffuse a medium is, right? So how spread out it is. So what does this look like? So we want to have positive entropy, which means that the energy is going to increase when that matter it spreads out. So whenever we're going from a solid to liquid or liquid to gas or solid to gas, any of those phase changes are going to involve positive entropy changes. And I'm sorry, my screen is really lagging here. So I hope this is not making everyone seasick as you're going through this. So other times when entropy is going to increase is when the energy increases when we're increasing temperature. So entropy is one of those things that if you just think through it, right, as we increase the temperature, those molecules are moving faster. It makes sense that they're going to be more spread out. There's going to be more energy involved with that. Whenever we have more moles of products compared to reactants, thinking about gases, that's also going to have a positive entropy. All right, let's see. Yeah, you know what? I think I probably have too many people on these slides, and maybe that's why. Let me try. Yeah, I should have made a copy. Let me do that right now. I apologize, everyone. Let's see. Okay, we'll try this out and then maybe there'll be less of a lag.
Yeah, and the lag hasn't been too bad on our end,
Okay.
I think,
Okay,
but this
good.
will get you alone in the slide deck. Remember, everyone, that slide deck is linked for you in the chat and in the video description.
Okay. I apologize. I'm getting to it now. Let's see. We'll hop back right into Unit 9. Continue asking those questions in the chat while I find my spot again, and then we'll keep going. All right, so that was just a little bit about entropy. Let's see. Yeah, here we go. So again, just understanding that's the dispersal or the spread of matter and energy. If you can remember situations where the entropy increases, that's really where you need to focus. And again, positive entropy is going to be thermodynamically favorable. All right, so let's see. And for some reason, it's still slow. That's a bummer. Okay.
And maybe close out of that other file real quick. That
Thank
will
you.
just get rid of that. But it's looking great on our end.
Okay.
Thanks for your patience.
Thank you. No, I appreciate it. Thank you. All right, let's see. Okay. I want to cover this misconception too, because this is something that is often shows up. So let's cover that. So if everything is favorable, right? So if I have a negative delta G or a Gibbs free energy value, you'd assume that it's going to proceed, right? The reaction's going to happen because it's favorable, right? And yes, it will proceed to equilibrium, but doesn't mean it's going to happen quickly. So we have to meet those certain conditions first. And you keep in mind, it's not going to happen. It could happen very slowly. Like the process of rusting is something that is be under kinetic control. So certain reactions are going to proceed so slowly, it's going to seem like nothing is happening, even though delta G is less than zero. This is another buzz phrase that tends to come up. This is known as kinetic control. So just know everything tells us that it's going to be favorable, yet seems like the reaction's not actually happening. That is known as kinetic control. Okay, equilibrium keeps coming back. This is another relationship you need to feel really comfortable with. Delta G equals delta H minus T delta S. A lot of times we'll have questions that are going to be theoretical with this. So if you have an increased temperature, how is that going to impact your delta H or delta G? So if you get stuck on things like that, throw in some arbitrary values, right? Just put in a number there and kind of see how that impacts everything else. That's the easiest way to do this quickly instead of just getting stuck trying to figure out, okay, how is this going to change? So yeah, and entropy is favorable when it is positive. Yeah. Yeah, let's go into coupled reactions next. So this just tells you all of those conditions that are favorable. Um, and let's see, we already talked about this. Still stuck. Let's see. Okay, coupled reactions. So this is basically when we take a process that would be unfavorable and we force it to happen. So we might use light or some kind of battery, some kind of other electrical source just to get this to actually occur. So let's see. I don't know why it's not. I think I just put too much content into this slide deck for you. Um, let's just move. I'll try to slow it down a little bit and see if my slide deck can keep up. Yeah, so a couple of reactions. Basically, we're gonna combine two reactions that share a common intermediate, right? That intermediate cancels out, and we add those up together to make that unfavorable process occur. Okay, so we'll use Hess's law where we're going to add up those two together. When we do that, we're going to add up our Gibbs free energy values. Again, the goal is to get a Gibbs free energy less than zero to make the overall process favorable. So on the AP test, what do you need to know about coupled reactions? You need to be able to pick two reactions that would work as a pair. You also need to be able to add up those delta G values to figure out how your final Gibbs free energy would be. So for example, this reaction here, we have a very positive delta G value. This is not going to happen naturally. So let's add in this reaction. So when we do this, our intermediate here is going to be sulfur. It's going to cancel out. And then we just add up our two delta G values to figure out that this is now going to have a delta G of negative 231, which again, we want a Gibbs free energy that's less than zero. So this shows us this is now a favorable process. So what should I know? Again, how to choose a pair of reactions. You're going to look for the shared intermediate and you're going to quickly add up those two values to make sure you get a negative delta G. You also just need to be able to add those up. All right, so that's coupled reactions. The other thing that everyone gets nervous about are is electrochemistry. So again, as someone mentioned earlier, keep in mind, this is 10% of the exam max. So you're not going to see more than, five multiple choice questions and maybe 2 points of an FRQ. So if Unit 9 is not something that you have spent any time on, you don't need to really stress about it tonight. These are the big takeaways for this. So we're gonna have two types of cells, right? We have the galvanic or voltaic cell. This is a favorable cell. You have to have a salt bridge in this, and you're gonna have the anodes and the cathodes separated from each other. Versus the electrolytic is going to be unfavorable. We have to have that battery in there to force this reaction to occur. Again, we still have reduction at the cathode, oxidation at the anode. And there are a whole bunch of mnemonics to help you with this. Um, which I think I shared. Let's see. Can't move as quickly as I'd want to. These are the equations associated with electrochemistry, so we'll go through this. Like I said earlier, this cell potential equation is not on the formula sheet. You can derive it on your own, but I recommend just memorizing this one. So the cell potential is equal to the cell potential at the cathode minus the cell potential at the anode. And again, if you can remember, an ox, a red cat, reduction happens at the cathode, oxidation happens at the anode. And you want to have a positive cell potential. The more positive it is, the more favorable the cell. And keep in mind, any of these cells, if the cell is at equilibrium, it's a dead battery. Okay, the goal with these cells is to make sure we are not at equilibrium, because otherwise, if we are at equilibrium, nothing's going to be happening in the cell. Um, the other equation you need to know from electrochemistry is delta G equals negative NFE. F is Faraday's constant. Again, E dot cell is the cell potential. And then N is going to be the moles of electrons from that redox equation. All right, let's see if it'll let me move. I am not sure why it's being so slow. All right, we'll just go back and forth. We'll make it work, right? That's what we do. All right, so overwhelmed. There are so many mnemonics to help you with all of this. So oil rig is hopefully one you've been learning since Unit 4, right? Oxidation is loss, reduction is gain. Electrons are counterintuitive, right? You add an electron and you gain negative charge. So take a moment to write this down so you don't make any silly mistakes tomorrow. Anox, red cat, oxidation at the anode, reduction at the cathode. Other thing to do is to remember how the electrons flow through that electrochemical cell. They're going to come to the cathode and move away from the anode. And when that happens, the cat gets fat. So the mass is going to accumulate at the cathode as the cell operates. The other things you need to know from electrochem, this was just an example from last year. Let's get into Faraday's constant. I'll put this in, I'll leave this in here. You guys have access to this. One of my friends and coached his daughters, Mr. Fair. You've probably watched some of Michael Farabow's videos. He just released this. So this is an FRQ you have not seen probably. So you can practice with that tonight. And I have all the answers in there too. And if we have time, we can go back to it as well. So that's their equation. All right, let's talk about Faraday's law. And I think I have slides in here. Do I? Okay, here we go. All right, electrolysis and Faraday's law. So this is a relationship that you will see, and it's really easy to actually pick up. So that's why I want to spend some time going through this. So I equals Q over T, where I is the current in amps, which is equivalent to 1 coulomb per second. Q is the amount of charge flowing through the cell, and T is the time the cell operates. So let's say I have a 10 amp current pass through a solution of nickel 2 chloride for 1 hour. What mass of nickel will be plated out? You may look at this and you're like, I have no idea how to do this. And it's actually fairly straightforward. So in this case, we're just going to calculate Q. That's going to be I times T. So that's going to be 3.6 times 10 to the fourth coulombs. But the question is, how do I translate that into mass of nickel? How do I take coulombs and change that into grams of a metal? And we're going to use stoichiometry to do this, which is what I like this concept. Doesn't everyone love stoic? Let me know in the comments, right? Like this if you do. Hopefully at this point you do enjoy stoichiometry. It's one of those easier things. Um, so when we use stoichiometry to solve, you're going to be going back to that initial redox equation. So we're going to be gaining 2 electrons, and we're going to use that in this relationship. So I want to convert from coulombs into mass of nickel, and I'm going to do that using Faraday's constant. So Faraday's constant, it's given to you, that's the coulombs per moles of electrons. I know that I have 2 moles of electrons involved in this reaction, and then I have my molar mass of nickel to find that final mass. No, you guys hate stoic, really? Normally AP students enjoy that by this point in the year. So I have built in more questions with Faraday's law and electrolysis in here. Other thing I want to just hit on, because this is another thing. Let me check the time. All right, we have 24 minutes. Non-standard conditions. So standard conditions for electrochem, it's a 1 molar solution or 1 atmospheric pressure for gases and temp of 298 Kelvin. So Q is 1, and the cell is dependent on the concentration of the pressures and the reactants of reactants and products. So that's the standard. So typically you will see, 298 Kelvin, 1 molar solution. If we have a change in that, it's known as non-standard. And we can't use Le Chatelier, it's not at equilibrium. So how do we determine kind of what that's going to look like, right? What is the cell potential going to look like at non-standard conditions? So what you need to know is just be able to relate back to Q. Okay, so if at standard conditions, Q is 1, because our concentration of products and reactants are both 1 molar. When Q is greater than 1, the cell's going to favor the products. So therefore, our cell potential is going to be less than the standard. When Q is less than 1, the cell's going to favor the reactants. And the cell potential is going to be greater than the original cell potential. So that's what you need to know about non-standard equations. I like to say this, you may have learned the Nernst equation in class. This will not be on the AP exam tomorrow. So you will not need to actually calculate the cell potential. You just might need to make a prediction about that cell potential. Okay, I think that was all of Unit 9. So let me back up and we'll go back into Unit 8 as well. Let's see. All right, Unit 8, everyone's least favorite least favorite unit. Um, all right. I appreciate all of you for being here. The chat is kind of cracking me up. Everyone is feeling cooked right now, guys. Everybody. That's part of this process, right? So I always tell my students, you are going to know, you know more than you think you do at this point. I think part of taking AP chemistry is acknowledging that there's so much to chemistry that you don't understand. Yeah. Okay, no, it actually is. That's very true. Everyone is uncooked. I like it. You might feel cooked, right? But you might be feeling overwhelmed, but you are at a better point than you actually think you are. Okay. Trust me on this. You have to trust me on this. We've been doing this for a long time. All right. So acid-base chemistry, easiest point you can get in all of this is just identifying acid-base conjugate pairs. So let's take a moment just to practice with that, right? Watch for that moving proton. The acid is going to donate it, the base is going to gain it. When the base gains it, it becomes a conjugate acid. When the acid loses that proton, it becomes a conjugate base. So this should be an easy point for you tomorrow. Let's see. I don't know why this is still lagging. So just make sure you keep track of that. These are the equations you need to know for acid-base chemistry. All of these. So keep in mind the concentration of H plus and concentration of OH minus. Those are not on the equation sheet. So just make sure you remember that so you don't have to move around the logs tomorrow. You're trying to save yourself time here. And there are going to be simple questions. And I know a lot of people are really nervous, right, about doing like acid base, weak acid, strong base equilibrium, or the pH of a buffer system. If you get a problem like that and you have no idea how to even attempt it, it's going to be worth like 2 points. Okay. Don't stress about those 2 points. Move on. And if you have a problem like that, and then you have to use the pH later in part C through E, write down a pH. Say, assuming the pH is 3.4, do the other calculations that you know how to do, and you will still get full credit. So error carries forward on the exam. So even if you did not know how to answer parts A and B, just write down a statement and keep going. Okay. Don't get overwhelmed by something like that. Let's see. It is just not wanting to cooperate tonight. Let's see. Let's talk about buffers though. That's another thing. Yeah, my slide deck is buffering right now, right? It's struggling a bit tonight. So basics of buffers. It's always going to be a weak acid plus a conjugate base or a weak base plus its conjugate acid. And basically a buffer system, when you have this combination, it's going to resist changes to its pH. So add in a strong acid, strong base, and you're not going to have a significant change in the pH right away. So this is all going to be based on the concentration of those pairs, and the higher the concentration, the higher that buffer can actually take in, the higher the buffer capacity. A 1-to-1 ratio is going to be ideal with that. Let's see. It just does not want to move at all. Let's see. So with that, the Henderson-Hasselbalch equation is the equation to know. And it's just this idea that the pH equals the pKa plus the log of the conjugate base compared to the initial concentration of that weak acid. We could also rewrite this for the conjugate acid compared to the concentration of the weak base. And this is important because when we're thinking about titrations, there's a certain situation where pH equals pKa. So let's look at that in just a second. So with titrations, just be familiar with these curves. And if you don't have these written down somewhere, please do that because this is the easy way to get points tomorrow. And you have to be careful because you'll see these graphs and you'll instantly get overwhelmed. And if you keep in mind these things that are always true for strong acid, strong base, or weak acid, strong base, you will get some points from that. So with a strong acid, strong base, these are the ones that you're most familiar with. You did these all the time in Chem 1. So we'll have strong acid, strong base, you'll have your equivalence point at a pH of 7 where your moles of acid are equal to your moles of base. Notice you don't have a half equivalence point with this type of titration, just the equivalence point, and the pH is always 7. So you should know those strong acids and strong bases, right? So let's look at our weak acids compared to our strong acid, strong base. So if I have a weak acid plus a strong base, that's the top one, or a weak base plus a strong acid, you'll see you'll have an area that it has a plateau, right? So that is going to be known as the buffer zone where we have neutralized half of the moles of acid or the moles of base. And this is important because when that happens, if we think back to the Henderson-Hasselbalch equation, the log of if our concentrations of our weak acid and our conjugate base are exactly the same, the log of 1 is 0, right? So when that happens, pH equals pKa. So every year there are questions on titrations. Every single year, you're going to have to either just find the volume from a burette. You got that, right? You're just subtracting. Or you're going to be given a titration curve and asked to find the pH of, or the pKa of that. When you have a weak acid plus strong base or weak base plus strong acid, the pH equals the pKa at that half equivalence point. Okay, so that's just that center point of that plateau. And then your equivalence point is going to be the vertical section. And that should be twice the half equivalence point. So just some easy things to keep in mind. We're thinking about that equivalence point. If we have the weak acid plus a strong base, that equivalence point is going to be slightly basic because a base is stronger than the acid, right? Weak base plus strong acid, again, the equivalence point is going to be slightly less than the pH of 7. It's going to be slightly acidic because of the strong acid. Let's see. Yeah, how do I perform a titration? So if you have a lab type question where you're asked to give a procedure, a simple procedure. Titration, you always have your solution of the known concentration in your burette, and you titrate that against the unknown solution, and that's going to be an Erlenmeyer underneath. You want to use an indicator. That's something actually I'll talk about. You want to pick an indicator with a pKa that's equal to the pH of your equivalence point, because that's going to change color right where you need it to. A lot of times you'll also have a situation where you just need to find the pH of something that's going to be basic. If that's the case, phenolphthalein is the indicator of choice, right? So phenolphthalein turns that bright pink in basic solutions and is clear in acidic solutions. I think, yeah. All right. Here are my acid base hacks just to make it a little bit easier. So pH equals pK at the half equivalence point. Don't waste any time doing any calculations. Just look at your graph and pull that number. It's just an estimate. You'll get points for that. The higher the Ka or the lower the pKa, the stronger the acid. When you're choosing a buffer, you have to find the conjugate acid base pair, and you can never have a strong acid or strong base in that. Okay, has to be weak. So be careful with that. And like I just said, choosing an indicator for titration, look for one that has a pKa that's close to the pH at that equivalence point. So you'll be given a list. Let's say it's a multiple choice question and you have a bunch of indicators with their pKas. Literally figure out which one is closest to the pH at the equivalence point of that reaction. All right. So this was just an example. We could do an example. I don't think we've done any FRQs. I apologize. I've been trying to cover as much as possible. We have 15 minutes left. So if I have a 25 milliliter sample of hydrofluoric acid titrated with sodium hydroxide, at the equivalence point of titration, what would the pH of the solution be? And a lot of these questions, right, you're just going to estimate. You don't have to spend any time doing those calculations. Just have an idea of what's going on. All right, try this out. What do you think? I did already show the answer, but let's see. All right, so with this, what do we have to know? We have to recognize that Sodium hydroxide is a strong base. So this is going to be a weak acid plus strong base titration. So pH is going to be greater than 7. It's going to be basic. Know these 7 strong acids. Know them, okay? You absolutely need these because you need to be able to identify what type of titration you're working with to answer questions like this, okay? Strong bases, those are going to be groups 1 and 2 with hydroxide. So just that's an easy way to identify those strong bases. I'd say don't focus on memorizing those. Focus on those 7 strong acids. All right. This is another type of titration problem that we often see. This is your sig fig question on this exam. You are just looking at this, you're making sure to estimate 1 digit past the smallest marking, and then you're just subtracting. So that's pretty straightforward. All right, all right, let's do this. So this is just an acid, I can't remember. I think this is actually from that titration problem. This is the problem with cutting and pasting these FRQs. It's hard to keep track of that. All right, so let's say we have this. We have given the concentration of potassium permanganate was 0.0235 molar. Calculate the number of moles of those manganate ions that were completely reacted with H2C2O4. So with this, you want to use the relationship MV equals moles. So the concentration is going to be equal to the moles of solute divided by the liters of solution. If we rearrange that, molarity times volume will give us the number of moles. This is so important just to keep that relationship in mind as you're doing a problem like this. So the endpoint has been reached. So that means the moles of the acid are going to be equal to the moles of base. We're just going to multiply these. Keeping in mind, you want to make sure your volume is always in liters. So I didn't talk about this, but that was our volume was 26.18 milliliters. We just multiply those two together, we have our moles. And that was it. All right, let's see. Let me check the chat again. Yeah, what's the volume? Great question. I should have showed you that, right? That was 26. Um, let's see. Yeah, what do you need to know about solubility for AP Chem? So I did that earlier. So solubility, focus on what is always soluble. So group 1, nitrates, ammonium, acetates. If you know that, you'll be fine. Let's see. Where did I get the liters? Yeah, I apologize. I did not cover that. Let's see. So when we did this, when we subtracted this, this had a volume of 26.18 milliliters. This is a good example of the type of lab data that you might have to derive. It's always going to be based on subtraction. You're either subtracting out the mass of something holding a substance, or you're looking at a burette and subtracting to find the volume. So we had a volume of 26.18 milliliters. I just converted that. Yeah, why do I use MV equals moles? So MV equals molarity times volume gives us our moles. We know that our moles because we're at the end point, our moles of KMnO4 are equal to the moles of H2C2O4. So that's why we can use that relationship here. Yeah, and M1V1 equals M2V2, or molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. That's a great relationship to keep in mind, but when we don't have a 1-to-1 ratio, right, you have to be careful with that. So do be careful with that. Yeah, Castro-Bear. So you don't even need to know the exceptions with solubility. So I don't even do the PMS Castro-Bear, but it is a good way to remember all of it if you need that for Gen Chem next year. Absorbance. Yeah, Beer's law. That's what absorbance is. And with absorbance, you might be given in one problem where you just have to calculate one of those. I think absorbance tends to show up, and a lot of students get it kind of thrown off by that because you haven't practiced with it. But it literally is just doing the algebra with that. You find the 3 variables in the problem and solve for the 4th one that's missing. Yeah. Yeah, and I did the big ideas at the beginning. So feel free to watch that at the beginning, but we can go back. We can go back to that. So big ideas are going to be things like uh, effective nuclear charge, Coulomb's law, polarizability, Q versus K. Let's see. IMF. Trying to think of what else we talked about here. We'll go back. Yeah, big ideas. Okay, labs. That's something that comes up. Yeah, lab techniques. So you need to be able to use logic to think through a situation. The more recent exams have had just quick questions saying, okay, given these materials, how would you calculate, this the density of this. Just that's probably too simple, but just knowing how to use the materials and explain, okay, a lot of times if you're given a lab situation, you need to find the mass, you need to find the moles, you need to find the volume, things like that. So just very simple concepts and making sure that you hit on all of that. Let's say you're asking you to find a specific quantity, make sure you get all of the numbers, the values you need to determine that quantity. Yeah, when do we use Henderson? Okay, HH compared to an ice table. So HH is good when you are looking at buffer solutions. So pH equals pKa and FRQ practice. Yeah. So yeah, a lot of you have asked for unit 7, so let's go ahead and do that. Let's see. So unit 7 is equilibrium. My guess is we probably want to do KSP, right? Oh, thank you for being here, AP Bio Penguins. All right, so what is equilibrium? And of course, it's going to freeze. All right, so equilibrium, rates of the forward and reverse reactions are equal. Concentration of products are unchanging. It does not mean we have equal amounts. So reaction quotient, we already talked about that. Let's skip. Let's see. Let's skip ahead. Ice tables. Yeah, let's do an ice table. I feel like I've seen that quite a few times. So let's go ahead and do that. Um, Yeah, and anything that I have not. Oh, is Marco a real dog? That is a good question. We might need a little Marco break. Um, with all of this, you have access to this slideshow. So you are welcome to look at all of these. And like I said, I linked each unit on that slide. I think it's slide 26, so you can jump around easily through that. So when we are determining the equilibrium concentrations, because a lot of people are like, when do I use ice? Equilibrium. Okay. So that's gonna ICE stands for initial change equilibrium. So let's say I have these initial concentrations for this very simple reaction, and I want to find my equilibrium concentrations. Let's see. So with this, you'll start with initial change versus equilibrium. I don't know what this is not working the way I want it to. I apologize. Um, Keeping in mind, you also have your K value. So K is going to be equal to the concentration of the products over the reactants raised to the power of their coefficients. So in this case, this is our simple reaction again. We're given our initial concentrations, which sometimes you'll be given that, sometimes you'll be asked to solve for that. So just being flexible with this, keeping track of what the question is asking for and what you're given, those are all such important skills. So in this case, we have our concentration of A and B, and we're asked to find our concentration of products at equilibrium. So with this, you're just going to use the ratios in the balanced equation to figure out the change, right? Let's see. Sorry about that. It's just not it's not working for me. I appreciate that's not it's working for you all hopefully, but it's just moving very slowly on my end. All right, so with this, we have a 1-to-1 ratio between A and B, so we're going to subtract X, but because we have that coefficient of 2 in front of C, we're going to add 2X to that. So at equilibrium, it's going to be whatever the initial was minus the change to get to equilibrium. So in the case of A and B, it's going to be 0.3 minus X versus C is going to be just 2X. Just doesn't want to work. So now we can relate that back to our K expression, our K value that we were given. K is the one exception where you do not have to have any units, which is great. So we'll have C squared over concentration of A times B, and this is where we negate X. So I mentioned that towards the beginning, one of those tips, you can always negate X on the AP exam. You're always going to assume that X is less than 5% and does not really impact the overall. So what that means is that we're just assuming that the change between the initial and the equilibrium is less than 5%. So we can just ignore that. Yes, your value is not going to be exact, but your readers don't care, okay? You can use that assumption on the entire exam. So now we can just easily solve without using the quadratic formula, and we'll find out that X is going to be equal to 4.5 times 10 to the minus fifth, and it was a concentration, right? So we want to find that concentration of C. Go back, multiply it by 2, and you will say the final concentration of product C would be 9.0 times 10 to the negative fifth. Okay, so this. All right, let's see. I think I added some requests for Le Chatelier, so let's talk about that. You have access to this. So you have that. No, you do not have to do quadratics on the exam. Nope, nope, nope. You might have to do it in your class. You might have to do it if you take Gen Chem next year. Yeah, you will definitely have to do it if you take Gen Chem, but thankfully you do not have to do it on the exam. Yeah. So when we think about Le Chatelier, the concentration, right? This is the one that's kind of intuitive. If the concentration of a reactant increases, the reaction is going to try to reverse that change, so we'll form more product. If we have more of our product, the reverse will be favored. When thinking about pressure, if the pressure decreases, the volume is going to increase, and we're going to shift to the side that has more moles. If the pressure increases, we're going to shift to the side that has fewer moles. Again, this makes sense, right? If the pressure is increasing, we have more things interacting. So we're going to shift to the side that has fewer, right? To negate that change. The whole idea of Le Chatelier is the reaction is going to try to counteract whatever change is happening to make it have the smallest impact on the overall system. All right, let's see. I think I had all right, temperature. So when we're thinking about changes in terms of temperature, and you have to think about where the heat is going to be. Is it going to be a reactant or a product in that reaction? An endothermic reaction is going to favor the products, while exothermic will favor the reactants if you're thinking about heat as a reactant or product. And then the opposite happens if the temperature decreases. So with Le Chatelier, knowing the differences between those, you will probably see a multiple choice question, maybe a portion of an FRQ asking you to predict how the system will shift at equilibrium. Yeah. All right, kinetics. So let's see. Um, we can jump around. Let's see. I think I wanted to do KSP with you all as well. Yeah. Let me take a sip of water. John, any chance Marco wants to say hi?
Yeah, I think he might. So actually, if you stop screen sharing, let me get him on, and we'll take a little Marco break in just a second. Hey everyone, Marco wanted to say hello. I got to take this blurring off. Otherwise, he's just going to disappear in the background. You know, it's starting to get past his bedtime lately. Come up here. Say hi to all the people. All these people. And actually give me a little cloud emoji or a sheep emoji in the chat. Here, give me your paw. And so, yeah, Marco was just blessing all the AP US government students earlier, wishing you all luck, telling you, you are not cooked. You are not cooked. You are undercooked. You are raw. You are in the freezer, not cooked on this AP exam. But you know what? It's past his bedtime. And actually, Corinne, this is a good reminder for us. We're almost at the end of our time tonight. I'm John from Marco Learning. If you've enjoyed this video, press that like button. And maybe, Corinne, we could go over some like final overarching things. It's 10 o'clock on the East Coast. We had somebody in the chat earlier said they're joining from China and their exams in 3 hours. What are some of those last minute tips that our students should take in these final few minutes here? And then, yeah, we'll stick around for a couple more minutes. And you know, it's just really important, as Marco said, you aren't cooked. You're going in with a year of hard work and preparation. Some of you have a lot of experience on AP exams. You're going to leverage that experience. You also know on the real AP Chem exam, you don't need to be perfect or anywhere close to it to get a great score. But Corinne, I'm going to let you kind of finish up these last few tips and pieces of advice as we go into tomorrow.
Yeah, absolutely. Thank you. I totally lost track of the time. A little bit of a chemistry nerd. I love doing this, and I appreciate all of you being so engaged with this. But as John just said, you've got this. You have learned so much this year, and hopefully you recognize that. If you don't recognize it now, you will after tomorrow. And at this point, sleep is more important than studying. So I encourage you to close your notes and get some sleep. Don't forget to eat tomorrow. Your exam is at noon. And if you have AP Gov right before, make sure you're packing multiple snacks so you can get through. That's a long day of testing. And food will make a big difference. You want to get to your test site early so you feel really comfortable. Grab those pencils, get everything prepped today so you're not rushing out the house really stressed tomorrow. And take some time to just laugh or cry with your fellow test takers tomorrow. You are all feeling the same way. You all have the same anxieties about this, but you all should feel confident going into tomorrow's test. And you want to get that 5, mention Coulombic attraction as much as possible. Again, that's a joke, but using those buzz phrases do get you the points that you need. Yeah. So thank you all for being here tonight. I hope this was helpful. And remember, that score does not define you. You should be proud of everything you have done this year. This is a tough class. And it's a tough class, especially when you are taking so many other AP classes. So be proud of all that you have learned and accomplished this year, and know that we're cheering you on from here.
Great. And maybe Corinne will do one last Marco salute. He's actually going to bed right now. So I think we'll get him on camera for one last goodbye. A little good night. You are not cooked kind of message. You ain't cooked. You're fine, everyone. You're fine, right? Say goodbye, everyone. Bye.